So today the topic is about the laser safety. So it will have some laser hazard into eye or skin, and also what are the standards for the laser safety issues. So this is a video. I hope you can see the video. This is endotracheal tube, and then actually there is a CO2 laser fiber inside. And then you can see that CO2 laser can cause a fire in this endotracheal tube, as you just see here. You can see from this video that how dangerous it can be when you are using the laser into the tube, which is going into your trachea. And then if there is a fire inside of your trachea, then you can imagine about the results from that. So it is very important for the laser safety. This is some paper reported by Yonsei University College of Medicine, reporting the case for the endotracheal tube firing in the OR during the CO2 laser assisted laryngeal microsurgery, which you have seen the video just before. This shows the telescopy showing some kind of here, you can see some irregular papillomatous lesions. And this is actually the vocal cord. And then the doctors were trying to remove that lesion by using the laser. And then it was actually the laser was showing some vaporization of the tissues. And then this can be removed, and then you can see the tissue under there. But during that process, this endotracheal tube was having the fire. So immediately, right after showing some kind of flume or smoke at the tip of the tube, they removed the endotracheal tube so that the patient was okay. However, if there was a late, then you can imagine about how that fire could cause the damage to the patient. So luckily, after that surgery, after that firing, they used another one, and then it was kind of showing the good results for the surgery. So after that kind of case report, people were trying to develop some new types of endotracheal tube, which can be used for the laser assisted surgery. So this one is a specialized laser resistance protected endotracheal tube, as you can see in the right side here. So this one has some kind of balloon covering this part. And this balloon is having this kind of bluish liquid. And this one is having kind of saline, but it has a color of the blue. So that when there is a firing from the laser tip here, and then this can be actually explode, and then it will have a leakage of the water with a bluish color, so that it can prevent any further firing, and also the clinician can quickly remove the tube from the patient. When you are using the laser pointer, the power is very low. It's about like 3 milliwatt. So it doesn't really cause any damage to the skin. However, if you are pointing the laser pointer to the eye, and then if that lasts for a little bit longer, then it can damage the retina of the eye. But mostly when you are using the laser pointer, especially it has a color of in the visible range, which is the green color or maybe red color laser, then our eyes are showing that blinking reflex. So we quickly close our eyes when something too bright light is coming. So it can actually prevent the damage to the retina from the laser pointer. When you have a ND-YAG laser, which has up to about 100 milliwatts, and this ND-YAG laser has the light in the wavelength of like 1045 or 1054, which is invisible. So that can be actually a problem because it doesn't actually, we cannot see the light. It's invisible light, but there is a laser. So our eyes cannot have a blinking reflex because we cannot actually detect. However, there is a laser is coming to your eye so that it can cause the damage to the eye. When you have a more powerful ND-YAG laser, which is about 10 watt, then actually it can burn your skin and also it can burn your clothes. And also if you have a Q-switched pulse ND-YAG laser, which can have a like nanosecond pulse, then even though that has a very short time for the pulse, but it can have a high power during that very short time, so that it can actually damage your tissue too with a multiple repetition of the pulses. So overall average output power can be high from the nanosecond ND-YAG laser. If you are using ND-YAG laser or CO2 laser with a 1 to 10 kilowatts, which is a very strong laser, those lasers can be used for the industrial purpose, which can be used for welding the metal. Then this one is really weapon, which you can actually see from the Star Wars or Star Trek, the movie. Pew, 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 and the blah, like that. The laser hazard can have either chemical or electrical or other secondary hazard too. The photo here, the powder, this one, is actually showing the rhodamine 6G. This is also actually used as a laser dye or the gain medium for the dye laser. And then it can be pumped by the second harmonic from the ND-YAG laser. So ND-YAG laser has a 1064. So second harmonic laser will have a 532, which is the green light showing on here. By giving this ND-YAG laser, this rhodamine 6G solution can be acted as the gain medium, and then it can emit another laser. However, this gain medium itself is very toxic. So this is very soluble to the water, but this solution itself is very corrosive to all the metals except for the stainless steel. And also cryogenic coolants hazard by the nitrogen gas, or when you are using the laser, it can make very noise. And also when you have a very high power supply for the pumping source, then it can actually generate X-ray. And also, if there is a problem in the optical pumps or lamp, then the explosion can also occur. And also, if there is a misuse, then there could be a fire can be also happening. This one is showing the video. So you can see here like this one, you can see some kind of smoke is coming from here. This one is actually from the amalgam, which is the material that are used to treat for the tooth caries. So you remove the caries from the tooth, and then you can fill that space with the amalgam, and then which is actually containing some mercury. So this amalgam is actually showing the mercury fume coming out from here, even though it's not actually easily visible by our eyes. But this video is showing that this amalgam can generate this mercury fume, which is toxic for our body. Um, so this one is showing the potential of the laser hazard when you are using the laser for the dental application. So for the dental application, we can use the laser to remove some part of the tooth enamel or the caries of the tooth. But during that process, if the patient had the amalgam kind of filled the caries, then they can actually cause the generation of the mercury fume. So another kind of laser hazard could be actually reported by this case. So human papillomavirus DNA in the CO2 laser generated plume of smoke and its consequences to the surgeon. So what is this? Is that the virus, which can be actually found in our body, those can be actually spreaded or contaminated to the surgeons. So when the surgeon is using the laser to remove the tissue, and then if the tissue contained virus, and then during that procedure, tissue can be ablated due to the water. Um, However, those virus could be actually remained without being damaged, so that this human papillomavirus DNA can be potentially released during the laser vaporization. In this case, this was actually from the genital human papillomavirus. It's like in Korean, kind of the human papillomavirus can be shown as a kind of samagi in Korean word on the skin. So trying to remove that part, the wart, and then during that process, this virus can be released, and then it can actually contaminate to the surgeon. Another kind of examples are shown in this example. So kind of the surgeon conducted a laryngeal microsurgery using the laser on the AIDS patient by having single suction tip and then simple surgical mask. And when they first got the HORLAB, which is a holmium laser inoculation of the prostate machine, the power was actually consuming too much electrical energy. Hi, Ji-hoon. So that was exceeding the operation room's power supply. So the results was that the power supply for the operation room was shut down. And then, of course, all the electrical facility in the operation room has been stopped, including patient's ventilator and also all the physiological signal monitoring devices. And then the surgeon is usually using alcohol pad to sterilize the lesion and also surround tissue. And then before that, the laser, not laser, but liver surgery has been started. However, the argon laser device did not work. So the surgeon drew back the laser device and checked and put it back, which is shown on these drapes on the skin, and waiting for the service engineer. And suddenly, the laser device emitted laser beam, but no one recognized at the moment. Soon after, the fire initiated on the alcohol wet drapes, and then people were, all shouting, "Oh my God, there's a fire!" So basically, when you are using the laser, especially when you are using the laser with invisible wavelength, then we need to be really careful for using the laser. So power and hazard, no specific threshold between the safe and the potentially hazardous or clearly dangerous beam. The factors deciding whether the laser will cause the hazard or not is going to be depending on the beam power and also how long the laser will be on, and then what is the distance between the laser source and then the target, and also whether your eye, whether the laser is coming to your eye or not. So in our body, maybe the most weak part of our body to the laser is going to be your eye retina. And then for the skin, you can imagine if there is a kind of burning, you can actually have some, kind of surgery on the skin for the plastic surgery to cover. However, when you have a damage to the retina, then it cannot be actually, replaced by any others. So that's why it is very important when you are using the laser source for the experiments, especially our lab and also Garlib, you need to actually have a proper protection for your body, especially your eyes. So it's better to wear the goggle, which you can find in the lab. For the eye hazard, if you have a deliberate staring the laser, even 1 milliwatt, which is very low, as I just mentioned, the laser pointer has about 3 milliwatts. So 1 milliwatt is very, very low laser beam, but even that 1 milliwatt beam, if you have a kind of continuous illumination to your eye, then it can make a spot in the retina and it can be damaged. For considering the aversion response, which is the eye blinking, that happens in about 0.25 seconds. So the blinking is kind of happening like 250 millisecond time response. So considering that your eye blinking reflex is working, then even 5 milliwatt beam can be tolerable, which means that when you have a 5 milliwatt laser showing to shining to somebody's eye, and if that has a color, that is important. If it has a color, then the other person can respond to the closing eyes within like 0.25 seconds. And in that case, it can be safe, even though there is an accident by shining the laser to other people's eye. However, if the laser power is beyond 10 milliwatt, in that case, the eye blinking is not enough so that it can have some damage to the retina. If you have more than 100 milliwatts, then definitely it will cause the damage to the retina. It will be also depending on the wavelength of the laser, which is because of the absorption by the eye. tissue. In this example, you are seeing from the UVC to the IRC wavelength range. So ultraviolet has three different regions, which we call as A and B and C. So UVA is the longest wavelength, and the UVB is second, and the UVC is basically shortest wavelength range. And as you can imagine, UVC is having highest power compared to the B and A because the wavelength is getting shorter, and the frequency increase, and then it has a higher energy. For the UV light, especially UVC and B, those are actually observed mostly by the surface of the eye, which is the cornea. So it can damage your cornea immediately. However, it will not go further into your eye because of the high absorption by the cornea itself. However, when you go for UVA range, and then it can actually transmit the cornea, and then it can be mostly observed by the lens in the eye. So that means that UVA range can damage your lens. If you are having the laser in the visible range, then it will be transparent for the cornea and also the lens, so that the light goes into your retina area. So if you have a visible range laser, the laser can be arrived at the surface of the retina, and then depending on the power, it can damage the retina, which can be really bad. If you have an NIR, near infrared range, which is maybe 780 to 1400 nanometer, these are also showing good transmittance through the cornea and lens, so that it can be reached to the retina. And then if you have a longer than NIR, so from 1.4 micrometer to like 1 millimeter range, IRB or IRC wavelength, then those wavelengths will be also mostly observed before the lens and the cornea. We do have the fluid field here and also inside, and then those fluid has a high contents of the water, so the longer wavelength is also going to be observed by the water in the eye. So here, as you can see, the cornea, if you have a damage on the cornea, that's also really bad. However, there is a chance that you can have a transplant from the donor if you can get. If there is a damage to the lens, now there is an artificial lens, so that you can also replace the lens. However, when you have a damage to the retina here, then you cannot have any replacement. So that's why it is very important, especially when you are using this range of the laser, because this range is not visible, so you have no idea whether the laser is on or off. And this wavelength range is able to come to the retina, so that it will give a damage to the retina. For the visible range, you do see the color, so you know, okay, there is a laser, so you can actually prepare yourself to be actually protected from the laser. However, for the NIR range, since you cannot see, there is a more higher chance that your eye can be exposed to the dangerous condition. So this one shows the more details from the previous one. So ultraviolet light for the UV A, B, C. So C is the shortest wavelength, and they can be mostly observed by the cornea. And the UVB is also observed by the cornea, but it can go a little bit deeper. UVC is going to be on the surface of cornea. UVB is within the cornea. UVA is able to transmit the cornea and then actually observed by the lens here. If you go to the infrared light, for the near IR, it is able to go through cornea, lens, and then vitreous fluid, and then reaching at the retina. And the far IR is going to be observed mostly by the cornea and also this fluid here. Showing another one examples for that. So for the visible range, due to our eye blinking reflex, so that it can protect our eyes from the laser. But for the NIR range, since we cannot actually realize whether there is a light is coming in or not, so that we are really exposed to the kind of laser hazard for this wavelength range. Another eye hazard from the light can be actually from the blue light. So blue light is longer than the UV light. However, if you have a kind of long exposure to the blue light, they can actually also give a damage to your eyes. So your skin and then your eyes are both can be affected by the long time exposure of the blue light. So as you probably all know that your cell phone and even your computer monitor has a kind of mode of like night mode or you know, kind of suppression of the blue color. So to protect your eyes and also to protect your skin. So if you have a long time exposure to the blue light, and then it can actually cause the aging process for kind of faster in the skin, so that your skin will get aged faster by the blue light, and also your eye can be actually having age-related macular degeneration. In Korean, 황반변성. That can be also happening from the blue light. So that's why during the summertime, especially with very strong sunlight, then it's better to have kind of sunglasses which can have a good protection from the UV and blue color. Those people who have the cataract, which is the clouded lens for the eye, in this case, the laser can be even more dangerous, because with the clear lens, the beam will be focused into the specific area for the retina. So it is actually interesting that even though we do have a large area of the retina on the eye, however, only a very small region is actually corresponding to the image that we are detecting from our eyes, and the other reasons are actually showing kind of, how can I say, the blurry image. So if you can actually imagine that when you are focusing your eyes to some specific subject, and then you do see actually some other part, however, those are not actually as clear as the focal area that you are looking at. However, when you have a cataract, which is basically clouded lens, then this is working as a kind of diffuser for the light. So the beam is coming in and it should be focused as the left top. However, instead of focus, it will have all different light will be spreaded into the area. So not only this region will be damaged, but the other parts of the retina will be also damaged in this case. The cataract is something like this one. Because of the cloudy lens, the image is not clear and it is kind of blurry, as you can see in this example. But luckily, for the cataract, it can be actually corrected by replacing the lens with the artificial lens. And also, when you are exposing your eye to the long time exposure to the sunlight, then photokeratitis, which is another word as a welder's flash or snow blindness. This is basically sunburn of the cornea. And then you can actually realize whether you got sunburn on the cornea until several hours after exposure. And the symptom will be basically tear, and then it will have a pain, and then you feel like you have a sand on the eye surface. So far, we have been talking about the eye hazard for the laser. Now we are moving to the skin. So skin, as you see, is the largest organ of the body, which covers our whole, the body. So that's why the skin has the greatest risk for the laser damage, because we have a large area that is exposed and which can be damaged by the laser, especially hand or face or head or arms. Those are basically, when you are not wearing the protective clothing, then they are exposed so that it can be damaged by the laser. So the laser effect on the tissue will be depending on the power density of the light and also absorption coefficient of the tissue, and then which will be depending on the light wavelength and how long the laser will be on for the skin. And also whether there is a fast circulation of the blood, which will determine the kind of heat dissipation from the laser, and also heat conduction in the affected area. You do not really feel strongly when the light laser is coming on your skin. However, when the power is going up to like 150 milliwatt, then you can feel that, oh, there's something. But according to our lab members who have done experiments using the laser that we have, we are not actually having very strong laser in our lab. We do have our lasers on the semiconductor laser for visible range, which is like 630 nanometers, and then maybe 730 or 780 nanometers, and then 850 nanometers, which is invisible range. And that can actually give up to 100 milliwatt. But after connecting to the optical fiber to the laser, the output power is reduced to up to 80 milliwatts from the 100 milliwatts. So that's kind of weak laser. However, even that 80 milliwatts, our lab member, previous lab member, was telling me that he could feel some kind of sense on the skin. Basically, there was kind of feeling of kind of hot. So not, it doesn't have to be 150 milliwatts, but if you are using the wavelength on the kind of high absorption by the tissue on the skin, which is kind of visible range, then you need to be careful for the skin protection. If the power is going like 500 milliwatts, then it will make a burn on the skin. Even if the person is a few meters away from the laser source. And this shows the examples of the laser caused a skin burn. So the immediately if it will cause some thermal injury to the skin, and then even if it doesn't cause the thermal injury because of it has a lower maybe power. However, if that has some kind of long time exposure, then you can have a photochemical effect, which is this kind of sunburn. And then that is basically excessive level of the UV radiation. So when you have a long-term exposure to the UV, then what happens is it can actually damage the skin. Here you can see the left one is kind of young skin, and for the aged skin is on the right side. So the overall, the thickness of the skin is thinner than the young skin. And also, you can see that the wrinkle is there. So those kind of thermo-epidermal junction, which is the layer of this. In the young skin, that is more kind of up and down like that. However, for the aged skin, that is becoming kind of flat. So here you can see the collagen, the dermis area, it has a high contents of the collagen. However, for the aged skin, those collagen is not actually shown on here. So to reverse this to the young skin, people are using the fractional laser, which you may heard it before. So in that case, you have a laser beam with a very tiny hole. So you're basically removing those parts. And then during the regeneration process, the collagen can actually be generated during the regeneration process. And then they can make a wrinkle to be flattened so that it becomes kind of flat, skin, which makes look young. When you have a UV range light, then the UV has a high energy, so that it can actually damage the DNA for the cell. So long time exposure to the UV can cause the skin cancer, which is from the DNA mutation. And then skin cancer is mostly happening to the people who has a bright color of the skin rather than dark color, because the melanin can absorb most of UV light. However, the kind of the light skin color people, they do not have a high contents of the melanin, so that it cannot protect your skin from the UV. So that's why skin cancer is mostly occurring those Caucasian the patient. And then summarizing the skin hazard depending on the wavelength. So for the UV range, it can cause the erythema and then skin cancer or accelerating skin aging. For the UVB or UVA or blue light, they can increase the pigmentation, which means that making more melanin on the surface. When you have a UVA range, they can also cause the photosensitive reactions, which is the same for the visible. And then when you have an infrared, it can also cause the skin burning, or it can make a skin to be dry. So for the infrared light, it can have a thermal damage, which is the skin burn. For the UV light, it can cause the photochemical reaction, so that change in the pigmentation, which is the melanin contents, and then erythema or skin cancer. So basic biological effects of the light are also summarized in this table. Depending on the wavelength range, the effects to the eye and effects to the skin are summarized in this table. So now take a look at the standards for the laser safety. So laser hazard classes are defined by their ability to produce damage in the exposed people. And then it is classified based on the concept of the AEL, which is the abbreviation of accessible emission limit. This AEL, accessible emission limit, is defined as a multiplication between maximum permissible exposure multiplied to the area of the limiting aperture. So LA is limiting aperture, and then MPE is a maximum power or maximum energy allowed for the specific wavelength range. So limiting aperture is basically depending on the factors such as the laser wavelength and also physical factors. For the eye case, we have the pupil, which can be changing its diameter depending on the light amount coming to the eye. So when the pupil is fully dilated, then it has a diameter of about 7 millimeters, which is quite large. And also, depending on the laser beam spot, so whether you have a focused laser beam or a large beam, so depending on that, the limiting aperture is determined. So here, beam hotspot, and then the hotspot means the brightest central area in the beam. So most cases, the laser beam is actually having Gaussian beam shape, which means that when you look at the intensity, it is showing from the center to the outside. So those hotspot is mostly by this full width half maximum value. So if this is like maybe 1 millimeter for each side, then this will be 2 millimeter. And then in that case, you can call this laser beam hotspot as a 2 millimeter. MPE is a maximum permissible exposure, and you can find this from the Wikipedia. If you type the maybe laser safety, and then the Wikipedia will show this graph. And here you can see 3 graphs, and then each of them are having different scale, different the unit. The left 2 is having exposure time versus energy density. The middle one is exposure time versus power density. And then the right one is showing wavelength to the energy density. So left 2 are showing also color lines, which are showing the wavelength of the light. Same thing here. And then the right side one is showing depending on the exposure time. So let's take a look at the example here. So when you look at the left one, when you have an exposure time as a 1 microsecond, and then you can make a line here. And then depending on the wavelength range, in the visible range, which is 400 to 700 nanometers, the green line here, corresponds to this point, which is slightly lower than the 1 microjoule per centimeter square. But if you go for a little bit longer IR range, then the maximum permissible exposure is a little bit higher. It is like tens of microjoule. So this graph is basically telling us that when you have a 1 microsecond laser pulse, and then if you are using visible range, then the maximum energy density is this one. You need to divide this energy density by the time, then you will have a power shown on here. So let's look at the middle one. So 1 microsecond is going to be this one. And then if you go up here, for the visible range, which is green color, the power density is less than 1 watt. So for the 1 microsecond exposure, you can have a maximum close to 1 watt per centimeter square. However, when you go for 1 second case, which is here, in that case, that corresponds to around here. And then this is 1 milliwatt. So a few milliwatts per second is okay. For more than a few milliwatts per centimeter square, then it will cause the damage to the your body. And here, these graphs were basically decided by highest power or highest energy density of the light source that is considered safe. So if you are having lower than this power or energy density, depending on the exposure time, then you can consider that as a safe. So for those who are using continuous wave laser, which means like long time exposure, then you need to look at maybe around here. So like 1000 seconds. And then if you have for our case, we are mostly using NIR, and then that corresponds to pink color here. Then that goes to around here, which is between 1 milliwatt to 10 milliwatts. So maybe around lower than 5 milliwatt, it is considered to be safe for the body. And then how this MPE has been measured is either from the cornea of the human eye or from the skin. So actually there are two categories. One is looking at the eye. The other one is considering the skin damage. And then either one of them, so of course for the eye, the MPE will be much lower compared with the skin exposure case. And then this MPE has been determined by 10% of the dose that has a 50% chance of creating damage. So what that means is, let's say, when you have a 1 second, and then when you have a visible range of the laser, and then if you have, let's say, 10 milliwatt per centimeter square, and then if this 10 milliwatt per centimeter square in the visible range caused 50% of the chance creating damage. Sorry, my shoulder is so painful. So if the 10 milliwatt per centimeter square for 1 second exposure of the laser using the visible range is causing damage to the skin, but the chance is 50%. So 50%, it may cause the damage, 50%, it may not. So if this 10 milliwatt is basically those that causing 50% chance of the damage. And then 10% from the 10 milliwatt, which is 1 milliwatt square for the 1 second for the visible range. This is the MPE value for the laser safety. So here, if you see, let's say maybe that is this is log scale, so maybe this is like 2 milliwatt per centimeter square for the 1 second for the visible range. Then you can imagine that 20 milliwatt per centimeter square at the 1 second of the visible range laser, this will have a 50% chance of the either damaging or not damaging the tissue. So this will be actually very, very safe by looking at the definition of this MPE. That's why when you are applying for the IRB, which is for the human experimental protocol, or ICOG, IACUC, which is for the animal, the care, animal study protocol. When you are using any device for the laser or light, and then you need to actually prove that your device is or your protocol is safe for the animal or human, then you need to use this kind of standard. So by looking at the values here, since we are using, let's say 10 milliwatt per centimeter square for the 1 hour experiment, and then that corresponds to maybe, I don't know, here. And then since the MPE value at the 1 hour for the wavelength in the visible range corresponds to a few milliwatt per centimeter square, so that our experimental setup can be considered to be safe for the animal or for the human too. There are a few classifications for the laser hazard, depending on the who classify them. So United States FDA has a 1, 2A, 2, 3A, 3B, and 4. And the NC, which is another standard, international standard, are having also 1, 2, 3A, 3B, and 4. And then another organization, IEC 60825-1, is having 1M, 2, 2M, 3R, 3B, 4. So those are all actually having similar, the definition for each classification. So when you look at the NC Z136.1, it has class 1, 2, 3A, and 3B, and 4. So class 1 is actually safe, even for the eye, in any condition. Class 2 is, in general, safe when human eye is blinking within 0.25 seconds. But so class 2 laser is actually considered to be safe, even though it is illuminated to the eye, but because of our blinking, the reflex, this class 2 laser can be considered as a safe. For the class 3A, they can cause some potential damage to the eye, especially when the light is illuminated to the eye by using the collecting optics, such as the microscope or binoculars. And the power level is 1 to 5 milliwatt range. Class 3B will cause the injury to the eye, and not only the direct beam, but specular reflection can also damage the eye. Class 4 is definitely giving eye damage, and also skin damage, and it can cause the fire. FDA classification or IEC 60824825 classifications are very similar to each other, but a little bit different, as you can see in this table. IEC is International Electrotechnical Commission Organization, and they are basically having a lot of standards related to the electrical device. And then FDA versus IEC. So now we need to have a way to protect laser from the eye damage. We have mentioned about this optical density, the definition before. So optical density here, how much of the incoming light is going to be observed by the lens for the goggles. So optical density, depending on the wavelength, can be from the log of the H sub 0, which is the anticipated worst case exposure, by MPE, which is maximum exposure, maximum permissible exposure of the laser. So let's look at the examples. So when you have an ND-YAG laser, which has a wavelength of the 1064 nanometer, and if that laser had 80 millijoule, and then maximum permissible exposure was like 5 times 10 to minus 6 joule per centimeter square, and the limiting aperture was 7 millimeter, which is considering our eye pupil diameter. So this is 7 millimeter diameter. So anticipated worst case exposure can be estimated by using the energy from the laser, which is the 80 millijoule, divided by the hotspot area, which is the area of this the aperture. So the radius is 3.5 millimeter. So you have a 0.35 centimeter pi r square, which is showing the area of this. So dividing energy with this area is providing you 0.21 joule per centimeter square. So the optical density is going to be 0.21 divided by MPE was this, which is 5 times 10 to minus 6, and then log of that. So that is giving you 4.6 at the 1064 nanometer wavelength. So what that means is you need to have your protective glass, and then it has a lens, and this lens should have OD more than 4.6. So let's look at this table again. So this is showing the conversion from optical density to the percentage of the transmittance. So since optical density is log 10 to 1 over t, or minus log 10 to t, and t is basically instant light intensity versus transmitted light intensity. So when the OD is 0, that means that the transmittance is 100%. When the OD is 1, then it is 10%, which is transmittance is 0.1 here. And then if the transmittance is 1%, then that's 0.01 over 1, which is 10 to minus 2. So that you have a 2 here. So if in the previous example, that was 4.6. So you need to have at least 5 for the OD. So that means that with that lens, this allows only 0.001% of the light intensity after this lens, then your eyes is protected from the laser beam. So this is how you kind of protect your eyes by selecting the 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 laser safety glasses. So when you have laser, so I guess you are all seeing this slide, not slide, but page. So when you search for the laser safety glasses, and then you can see variety of the laser safety glasses can be found. And then depending on the shape, it looks very weird for this one. And the other one looks kind of fashionable also. So let's say if you selected this one, and then this one is basically designed for femtosecond ND-YAG laser. And then you can see here optical density shown on here. And then here you see that depending on the wavelength, it has a different.
Sorry, Professor.
Uh-huh.
We do not see anything.
Oh, okay. Let me reshare. So now do you see the web page? Okay. So when you look at the specifications for those glasses, and then you can also see the visual light transmission is 14%, which is very low. However, you will be able to see things throughout these glasses. However, for the wavelength, which is shown on here as optical density, so depending on the wavelength, the optical density values are different. So you need to choose the laser safety glass depending on which wavelength of the laser you are using. So let's say for the NIR, which in our case, if you have a shorter than the 850 nanometer, that is OD is 5, higher than 5. If you have a 850 to 1080 nanometer, the optical density is 7. So this is showing that 5 was 0.001%. This one will be 0.00001% of the transmission. So you need to look at these optical density value for the each laser safety glass to purchase the proper one for your application. Okay, so this is the end of the this semester's material, and then I will kind of go over all the materials that we cover. Especially, I'm sure you all forgot about the early time materials, so that we need to have some study again for the previous material, and then we will have a final exam. However, I was thinking about the final exam, and then how can we have a exam in the class? I think that it is possible to have an exam in the class, but maybe not, depending on the policy of the school. So I need to find out whether it is possible to have a class test in the class. Since we have only 6 So I think that it is possible. But for the final exam questions, I want to ask you to make the questions. So you may wonder, oh, what that mean? So basically, I want to give, not giving something, but I want to ask all of you to make a questions. So each of you are making questions, maybe up to 20 questions. So the question type can be just up to you. So you can have a question like, maybe choose answer from the following examples, 1, 2, 3, 4, and then the right answer is like 3, like that. Or you can make a question like, let's say, optical density is, blank, and then, or maybe a simple question, what is the definition of the optical density? And then we need to answer, okay, optical density is log, 1 over t, like that. Or you can have a more harder question, such as like, what is the inverse Bremsstrahlung? So we know that Bremsstrahlung is generating the photon from the reduction of the kinetic energy. But inverse Bremsstrahlung is having the light energy and then accelerating the free electron speed. So something like that. So think yourself as a professor, you are the instructor for this class, and then generating questions for the 20 questions throughout the whole this semester materials. And then I will collect those 20 questions from each of you. And then I will pick up 20 questions from your questions. So which will be 1, 2, 3, 4, 5, 6. So I will have 220 questions from 6 students. And then I will choose 20 from 120 questions. So you can share, not share, but after I collecting all the 20 questions from each of you, then I will share 120 questions to all of you so that you can prepare, and then you can focus on studying those 120 questions. And then basically you can answer 20 questions, which you may think that, oh, they will be super good because, as long as you understand about 120 questions, then you will get the perfect score. But unfortunately, everybody thinks that. But unfortunately, even in that case, there are students who cannot make 100% score. I don't know why. So now we have a, let's say, let's look at the time. So today is June 1st, and then June 14 is the week for the midterm exam, final exam. But we decided to have a little bit earlier termination of the class. So I like to have an exam on June 10th, which is actually only 10 days left. So that means at least, when do you want to have a final 120 questions? Because you need to have some time to study for the 120 questions before the final exam.
It is better to be before the weekend.
That means you need to give me 20 questions before maybe this Saturday.
Yeah.
And then I can give you 120 questions maybe Saturday night, by Saturday night. And then you can have a time for Sunday, Monday, Tuesday, Wednesday, Thursday, like that. That's actually 4 days only. But don't make a question to be too easy. Let's say like, what can be a good example? I don't know. What can be a good example for too easy question? But I will just make it everything depending on you. So when you are studying, you will find out which one is important and then focus on that and then make a questions. Okay, so send me your 20 questions by Saturday. And then by Friday, by Saturday. By Saturday, the midnight, and then 120 questions will be delivered to you in the morning of Sunday. And then I will actually go over questions quickly, and then I will remove questions that seems like too obvious or too easy. And then, so it can be maybe less than 120 questions. And then if there are something that you are missing for the 3 years, then maybe I can add 1 or 2 kind of important questions if you did not mention in the question. Okay. So do you agree for that schedule? Okay.
Sorry, Professor.
Uh-huh.
Can we divide the topics between us and make the question?
Not really. Because as you can now see, the purpose of asking you to make a question is to make you study. If I give you like each one has a different section, then I'm sure you will study only that section, right? And then the other section, you will just looking at the questions. So don't think your professor is not smart. I'm smart.
But maybe we will repeat the question.
I know. That's why kind of similar question means that actually that part is important. So it doesn't have to be like all different questions, but I can see that whether you maybe were discussing with other members that, okay, let's make this question to be safe. They cannot happen. So the main purpose for this way is making you to actually study for the whole material, so that at least you have some idea about what are the important things, so that you can make a question from the materials. And then choose like 20 questions from out of 120. And then I'm sure there will be many questions will be overlapping each other in terms of the contents. But that's okay, because that means that many of you are considering that question is important. So send me your kind of 20 questions by Saturday night, and then I will deliver 120 questions to you by Sunday morning. But if there are many questions are kind of similar questions, then I will delete. And then you may have only 100 questions, or you may have only 80 questions like that, which can be actually more better for you to study until the Thursday. And then I will check with the staff whether it is possible to have a in-class exam. And if not, then I have to think about how can we, proceed for the final exam. Any questions about the final exam? No? Okay. Then prepare 20 questions by Saturday, and then you can send me by email to me. Okay.
Professor,
Yes.
in our question, we have to make there are some standard form, such as subjective problem or objective
But that's what
problem.
I'm saying. You can choose any format. It can be like choosing an answer from 4 answers, or it can be making a filling the blank, or it can be a short question asking you to write short sentence like that. So you can decide the format also, but just don't make it too simple or too easy. Jihoon, any question or suggestion? Not really? Okay. All right. Then
Professor, exam time in like
maybe
a
1
class
hour
time?
and 1 hour 20 minutes. Yeah, so I'm sure 20 questions will be answered within 1 hour and 20 minutes. Okay. All right, thank you so much. And then I will wait for your questions by Saturday midnight, but we will have a one more class on this Thursday to go over the whole material quickly for which one is important part like that. All right, thank you, and then have a good day today.
Thank
Bye,
you,
everyone.
Professor.
Thank you, Professor.
Okay.
Thank you, Professor.
All right.